Okay, let's take a look at what's important in section 2.2. These modes of operation, yeah, they're important, but we're only really going to be doing one, and it's this protected mode. So you can read about these others, but we're not gonna mess with them. Everything we're going to do is going to be in protected mode. Part of that's because of the time we have for this class. Part of it is just because this is the most important one. Let's come on down. Address space. Here's what we're looking at. Since we're running in protected mode, you need to understand that every program running in protected mode thinks it has 4 gigabytes of RAM, even if there's not that much on the machine. Alright, this section is talking about the registers in the machine. Remember, those are the tiny little memory areas that are actually on the CPU. You're going to get to know these very well, so now's a good time to start. Learn their names. Here they are. We won't be using these down here, these segment registers, very much, but the others we will be. So as you're going through that, realize that, okay, we've got general purpose ones. That's what all of these are. And some of those general purpose ones we can divide up like this. For example, the EAX register, I can use all 32 bits of it. I can just use the lower 16 bits of it. And out of those 16 bits, I can take the upper 8 of these 16 or the lower 8 of these 16. Now that works on the EAX, the EBX, the ECX, the EDX. We can divide these up over here too, but not to the extent we can these 4. But they're all general purpose registers. As we come on down, this is still talking about dividing those registers up. Now the ones that we can't divide up this much, we can split them in half. So for instance, the ESI register, we can use just the lower 16 bits of it, and so on with these others. Some of these registers have special uses. Look over this, but don't worry about it a whole lot right now. We're going to get into those in detail as we start programming. Same way with the segment registers. Get an idea of what they are, but we'll get into it later, to some extent anyway. The instruction pointer we've already talked about. It's a special register that contains the address of the next instruction to be executed. The flags register, know that it's there, and know what you don't have to know what these control flags are right now, these status flags. Are they important? Yes, they are, but we won't get to them until we start writing if statements in assembly. Then we're going to use these a whole lot. Just be aware they're there. These registers, the MMX, the XMM, we're not going to talk about at all at any time during this class. The floating point unit, on the other hand, let's take a look at it. Even though we're not going to get into the actual programming of this, it's beyond the time and scope of what we've got to do. Please understand that this is where, if you're dealing with real numbers like 18.75 and you're doing arithmetic with those kinds of values, this is where it occurs. Memory management, once again, we're only talking about protected mode. So don't really worry about this. Don't really worry about this. We're going to be dealing with protected mode only. And speaking of material we're skipping, we're going to skip section 2.3 entirely. It has to do with 64-bit processors, and like I've mentioned before, we're going to work with 32-bit processors. So skip section 2.3. Section 2.4 is dealing with some pretty important hardware. The first of which is the motherboard. So as you're looking through this section, get a good idea of what these things are. They're all important pieces of the motherboard. Read their descriptions. Take a look at this diagram down here. And just get an idea of where these different things come into play. This is a drawing of an older Intel motherboard. Here's what an actual motherboard looks like. A little more detail than what the book shows. Down here is where you would install your RAM. Up here, these are for cards that you would add to your machine so that you could add functionality. Here's the CPU. Don't know if you can see it, but there's a bunch of little wires coming off that CPU. And if we could zoom in on this motherboard more, you'd see that most of what you just see is green right here are actually little wires that are made onto the motherboard. This shot is zoomed in on some of those little wires I'm talking about. A human cannot make these boards. They're all done by robots. All of these little dots that you see are solder connections where there's components hooked to these little wires. Here's another shot of a different motherboard. Looks like a small city. Here's the underside of a CPU. Notice all these little pins. They're really tiny. There's hundreds of them. They plug into the motherboard and can access all the components on the motherboard. Everything pretty much runs through the CPU. Various kinds of memory in a computer. I do want you to know the difference in these. DRAM, well, that's what we call RAM. Here's your L1 cache type memory, video memory, and this CMOS RAM, that's what most people refer to as just the BIOS on the motherboard. It remembers the information about the hard drives you have installed and different settings on your computer. ROM up here, that kind of memory is burned into chips and you can't change it. Think about a calculator. A lot of what's inside of a calculator is in the form of ROM that the creators of the calculator programmed, but they don't want you changing it. Let's look at section 2.5 and we'll wrap this thing up. Finally, section 2.5 is talking about input-output, otherwise known as I/O. There are several different levels of that. What we as high-level programmers are used to is this top level. In other words, in C++, when you say cout, hello world, or in Java, when you say system out println, hello world, you're dealing with input-output at a high level, which means you don't have to worry about the details. The next level down, the operating system. Think about Windows. It has to perform at a lower level. When you save stuff to a file up here at a high level, Windows has to open that file and save the data into the file at a much lower level. Be glad that you don't have to do that as a high-level programmer. And then we get down here to the BIOS level. That's where you're talking directly to the hardware. So that's where device drivers come in. They are the go-between between the operating system and the hardware. When you insert a flash drive into your computer, there's a device driver that lets that flash drive interact with the operating system and ultimately your program. And this is interesting right here. What has to happen just to print a string on the screen? Here's a diagram of just different levels of access for input-output. Here's our C++ program, operating system, BIOS, hardware. This part of the text down here is trying to get you to realize that the further down you go, the closer you get to the hardware, the more specific the programming has to be. Most of our high-level programs can't do this level 0. They can't do all of the BIOS, but assembly language can. it can access any of those different levels of input-output. What do you have to worry about, though? Again, the closer you get to the hardware, the more specific that assembly language program is, which means it'll only run on certain machines. As you go up the ladder here, C++ program should be able to run on a bunch of different machines. Read this part down here. Get in your mind that we're dealing with a type of language that can access any level of input-output, including directly talking to the hardware. That gives us a lot of power, but it also means we can mess things up if we don't know what we're doing.